Hi guys, this is Derek here. I will be talking about faithfulness tests for natural language explanations. This paper has been accepted at ACL. I think I'll have to double check. But the idea is like if you have of a question, and then if you have a chain of thought explanation, and then if you have an answer, um, people usually think the chain of thought will be a direct reflection of the answer, but that is not necessarily the case. Usually what the model generates in terms of like the chain of thought and the actual answer are generated independently, and they happen to explain each other very well. And what the paper is trying to do is talk about like the faithfulness tests for natural language explanations. So the idea is like if you change the chain of thought prompt in the input, then this should also affect the output as well. And they talk about two tests, counterfactual input editor, and then like an input, they call it the counterfactual test. And the second is the input reconstruction test, and I'll be giving examples on what this exactly means. So in a natural language explanation task, you have a premise and then a hypothesis, and then you have a prediction. Not necessarily, but more or less you have some input and then you have a prediction. The main data set that they, or like the first data set they use is actually the NLI data set, which has a premise, hypothesis, and then a prediction. Prediction being like it has to follow one of the three relationships. Entailment, like the premise entails the hypothesis. A contradiction, the hypothesis contradicts the premise. And neutral, neither entailment nor contradiction. So here, if you see like a man in a black suit, white shirt, and black bow tie playing an instrument with the rest of his symphony surrounding him, and the hypothesis is a tall person in a suit, that is neutral, because they're not necessarily like contradicting anything or saying that like A like entails B. So the natural language explanation, this is generated by the model. It's the explanation they have is like not all men are tall, and the model outputs neutral. So the idea is like if we change the input, then if the model was actually if the model was actually basing the if the explanation was actually a reflection of the decision-making process of the model, then that change should also be reflected in the output. So if the input was changed and the model is here, and then the output, right? If this was changed a little, then this should also be changed, right? So they talk about, this is where the concept of faithfulness comes in. Faithfulness is like it reflects the decision-making process of the model, and unfaithful means like it does not reflect the decision-making process of the model. So what this paper is trying to say that like these explanations are unfaithful, and they show that by these two tests, the counterfactual test and then the input reconstruction test. So the counterfactual test is like you have either like a random like perturbation, like a change, you add the word blue or etc., and see if that explanation is reflected in the natural language explanation. In the input reconstruction, what they do is like they have the natural language explanation, and then they like use it as a premise, and then the hypothesis, and see, and their logic is like if the model is consistent, if this is actually a representation of this premise and hypothesis, then this natural language explanation should also be reflected, generate the same prediction, but it does not. So in our example here, like many people standing outside of a place talking to each other in front of a building that has a sign that says High Point, right? And the hypothesis is the people are having a chat before going into the work building. So it's neutral because like they're just talking to each other and they're just having a chat. You know, it doesn't necessarily entail contradict. So it's neutral, right? That makes sense. So this is correct. So what this does, what they're trying to do in the input reconstruction test, you get the natural language explanation. Just people are talking, so that's the first part. They are having a chat, right? So that's the second part. So they have these two parts, and then they feed this into the model, and the prediction should result in neutral, but it does not. And also, like people are talking is a rephrasing of having a chat. Yeah, that's correct. But like the reasons in the NLE for the original instance led to a different prediction. So this is like a mismatch here. And then we can like witness like why this is happening. Or like I guess like we can pinpoint that this is actually a problem, because the literature talks about whether here like show that certain widely deployed explainability approaches that provide saliency maps, you know, like with importance scores for each part of the input, words or superpixels, can even be independent of the training data or of the model parameters. So it's basically saying saliency maps are like unpredictable. And what they're trying to suggest is that they have a better like test to actually like say that these these saliency maps do not actually provide any necessarily an insight, because it's not these ablations or changes are not robust. So here, so this is an example. Yeah, like we said, a tall person in a blue suit, a man in a black suit. So you can't, the assumption is like I guess you can have a black suit and a blue suit, you know, the same person, right? So that's why it results in a contradiction, and this is fine. But what's off, why they call this a mismatch, is because the explanation of blue should somehow end up in the natural language explanation, which is generated by the model. Like inserted word blue is not part of NLE, but change the prediction. So what they do is, yeah, this is like the data set. I want to talk a little bit more about the actual examples so you actually understand what's going on. This is more in the appendix actually. So yeah, you have the COS-E dataset. The EAS and ELIA dataset we talked about, you have a premise and then a hypothesis. The COS-E dataset, you have a question and then you have a multiple choice: poverty, debt, bankruptcy, you know, and then it picks that, right? And then it generates an explanation. So the COM-VE, you have sentence 1 and then sentence 2, and then the prediction is like you predict the first sentence. Basically, the job of the model is try to pick something that pick a sentence, either sentence 1 or 2, that actually contradicts. Like everybody hates paying taxes, right? So the natural language explanation is paying taxes is a good thing. I guess this is their logic. And what they do is like they have rather a random insertion baseline, or they have a counterfactual editor, which does they insert it more precisely. I guess I have to like understand it a little bit better. But just to go over the examples, like here, this is the same sentence, but they add the word increasingly, and then the model predicts bankruptcy, and the explanation is bankruptcy is the only option that is a result of spending money. Kind of true, but like the word increasingly is not part of the natural language explanation. So, you have to wonder, like, yeah, you have the input, and then if you have a different output, if you let's say you have an input and then you have an output, right? But if you change the input slightly, then this should also be reflected in the output, but it's not. So that's why it's saying like this is a mismatch. So here, this is another sentence like everybody hates paying taxes, nobody ardently hates paying taxes. So the word ardently doesn't also appear in the natural language explanation, and it changes the label. So the fact that it changes the label and it changes in the natural language explanation, and the original input, the change in the input is not reflected in the explanation, shows that this is a mismatch. Yeah. So here, a man wearing glasses and a ragged costume is playing a Jaguar electric guitar and singing with the accomplishment and accompaniment of a drummer. A man with glasses and a disheveled outfit is playing a guitar and singing along with a semi-formal drummer, right? So the prediction is neutral. So you can see like the prediction has been flipped. Not all ragged customers are disheveled. Yeah, I guess, but like the word semi-formal is also not appearing here. So you get the idea, right? So here, if you look at the counterfactual editor, so like this is the original instance. This is the instance after test intervention. They add outside so many times together, all of which do not appear in the actual natural language explanation, but the labels are flipped. So if you see here, first sentence is changed to second sentence, and then the table is changed to backpack. So yeah, this is what they're trying to do, and the models they use is like T5, but they have variations of it. They have 4 different variations. So here I will talk about, well, they have 2 types, 2 types. Let me see. You have a joint model MT, or like a single task using separate model ST, right? You have rationalizing models, reasoning models, RA and RE, right? What does this mean? So joint model means I think it inputs the is a joint model for task prediction and NLE generation, and then it generates the explanation and then the label, right? For the separate models, you have one that's for explanation, and then this explanation is fed into the prediction model. So yeah, so you can see like this is the same, and then it generates an output. So yeah, you have an explanation here, and then you have a prediction task as well. So what is RE and RA? So RE is a reasoning model, and it generates explanation first and then the label next. So if you have like a premise here, right, a man is playing the guitar on stage, hypothesis is a person is performing music, right? And then what it outputs is like label, entailment, and explanation is because playing the guitar is a form of performing music, right? But the difference in a rationalizing model is the label is actually fed into the inputs. So here, if you see the label here is an input, and then here in the output you just have an explanation like the NLE that it was talking about. So explanation is generated conditioned on a label. This is like the term they use. Conditioned on a label, the model generates NLEs that explicitly reflect the target predicted class. So this is the difference. So here, that's why you have 4 different models, MTRE, MTRA, MTRE, MTRA, STRE, sorry. And then these are the models in question. And then what it does is for the input, they either randomly haven't changed the value or like they edit it using a counterfactual editor, which is I guess has more precision, and then MTRE rand edit is like a accumulation of both. So this the counter column indicates like the editor's success in finding inserts that change the model's prediction. So it's basically saying like, can the model, like the editor's success, this editor, right, in finding inserts that change the model's prediction. For this part, the counter on faith one, what this is saying, like these numbers all mean like among the instances where the prediction was changed. So this is a denominator, and then presents the percentage of instances where the inserted text was not found in the associated NLE. So yeah, so this is more related to what we see here. Like you see blue, and then blue is not in the actual NLEs. So if you find only the values where the prediction does flip, we can see, like, I guess some of them actually reflect the NLE, but there are also cases where it doesn't reflect NLE. So the percentage of that would be this, like 60% of them among the ones that have been labeled do not have the actual random edits in the explanation. And then the total unfaith presents like the percentage of instances where the prediction was changed, and the inserted text was not found. So it's a combination of where you have changed, and then the inserted text was not found in the associate NLE. I guess like the denominator being like every instance. So yeah. And then they have the ESNLI dataset, COSI dataset, COMB, and they have these variations. So this is a counterfactual test where we talked about here. So you have, they have an ablation, and then see like how is this reflected. So for the input reconstruction test, for this table, what it's talking about, it shows a percentage of instances for which we managed to form a reconstructed input. So I think like their counterfactual editor like is not necessarily capable of forming a reconstructed input. So for here, I guess they're able to do it all the time, but here they're only able to succeed like 45% of the time. And here the total percent unfaithful shows the total percentage of unfaithful NLEs found among instances in the test set, right? So it's looking for these type of examples where you feed in the NLE, right? And then people are talking, they're having a chat. It flips the label, and then, yeah, the NLE, the reasons in the NLE lead to a different prediction, right? So like this should also lead to neutral, but yeah, it flips. So yeah, the total unfaith shows the total percentage of unfaithful NLEs found among all instances in the test set of each data set. So yeah, what they do is like they're trying to say that like first, we observe that when the random baseline words find that change the prediction of the model, the words are more often not found in the corresponding NLE compared to the counterfactual editor. We conjecture that this is because the randomly selected words are rare for the dataset compared to the words that the editor learns to insert. So another conclusion they found was like, second, the counterfactual editor is better at finding words that lead to a change in the model's prediction, which in turn results in a higher percentage of unfaithful instances in general. So yeah, yeah, I think this is talking about numbers, like how slightly different. So their contribution is like they're introducing two tests to evaluate the faithfulness of NLE models. We find that all 4 high-level setups of NLE models are prone to generate unfaithful NLEs, so they are capable of entering. So reinforcing the need for proof of faithfulness. So what they're doing is like they're indicating that this is a problem. Yeah, they don't necessarily come up with a solution, and they talk about the limitations here. Yeah. So, I mean, it's not mentioned here in the limitations, but it'd be nice if they actually have a solution. But this is really hard because, like, LLMs are naturally like a black box, and no one really understands, like, why. They're so also incredibly huge, and there's so many parameters, and they don't understand why certain knobs are changed and how that actually reflects the internal reasoning. So if I can do something similar, that would be interesting. I will try to work on how to add like lexical variation into the input and like have more systematic things, but we'll see. Yeah, thank you so much for listening.